All right, let's take a look at the enthalpy of neutralization. We remember here that enthalpy is our delta H. We're looking at neutralization, which is just a particular reaction. We know that our delta H is going to be, by definition, our heat at constant pressure. This is also called Q sub P, normalized to the number of moles. So we're going to take this Q sub P and divide it by the number of moles that have reacted to get our enthalpy. That's our job in this reaction to start. And then we're going to do some other things with it. Get a delta H and a delta S. Our reaction here is HCl plus NaOH goes into H2O plus NaCl. We can look at this in a different way. We can also look at this as H plus OH minus goes into H2O. And we can recognize that this is also the inverse of the autoionization of water. If we think about the autoionization of water, that is water dissociating into H plus OH minus. We can consider that as well in terms of the hydronium and make two waters dissociate into a H3O plus OH minus. This is relevant because we know the value for the equilibrium constant for the autoionization of water. At room temperature, we know this is Kw, and this is 1 times 10 to the minus 14. Please realize that the reaction that we are doing is the inverse. We are looking at the complete inverse of the autoionization of water. Now, we need the heat, and our heat is Q. When we do heat, we're looking at the equation of heat is equal to the mass times the specific heat capacity multiplied by the delta T, where the specific heat capacity, we're going to assume that this is for our NaCl solution, because that's what we have here at the end is in fact 1 molar sodium chloride, and the value of C sub S here is 3.87 joules per gram degree Celsius. Back at your first thermodynamics chapter in Chem 111, if you're stuck on that, our delta T here is always going to be T final minus T initial. And when we measure heats, we never measure the heat for the actual reaction. That's pretty much undoable. What in fact instead is we measure the heat for the solution. So the Q that we're going to get here is for our solution at the end. And our solution at the end is actually this stuff, is what's going to absorb the heat. So what are we doing here? Well, remember we took 25 mils of our 2 molar sodium hydroxide, our 25 mils of our 2 molar HCl, we mixed them together, we stirred them up with a thermometer, and we noticed our heat went up. Remembering here that the heat that we are considering, the Q that we are considering, is for the solution, not for the reaction. We're going to need it for the reaction in a moment. So what are we going to do? Well, if we go to our data, remember that this is going to be 25 mils. Our total volume here is going to be 50 mils. We have to take, and when we do this, we're going to use the mass. Please remember, if we're going to go from our volume to our mass, we're going to need the density. T initial is going to be the room temperature of our acid and base. Just average them together if they're different. T final is what you're going to measure after the reaction has maximized its temperature, and our delta T is going to be the difference. When you take and you plug this in, you're going to get a Q value of your solution. Remember, the first law of thermodynamics tells us that heat or energy is conserved, which tells us that Q of our solution plus Q of our reaction is equal to 0. The reaction is what's actually producing the heat. The solution is what is absorbing the heat. So you're going to find that Q solution is going to be positive. Our Q of the reaction is simply going to be a negative of that value. We're going to need to know how many moles we have if we're going to get delta H. We're going to do this in terms of either moles of water or moles of HCl. Please remember that the volume in liters multiplied by the molarity is going to equal moles. the hydroxide and the acid are 1-to-1, so you can use either one. Make sure at the end when you do this, you're going to put this in kilojoules per mole and make sure that your sign is correct. So with that, you have your delta H. Now, going on to our thermodynamics chapter for the last bit of this. So here we know that the reaction for today's lab is strong acid plus strong base gives us water. But we also know that the autoionization reaction for water is the reverse of this. So here, if we know that water plus water is going to go into hydronium plus hydroxide, and remember this is the reaction that we use to generate our pH scale. We know what the Kw, we call this Kw because it's for water. We know what the Kw is for this reaction. So look that up. Well, if the reaction that we are doing, so this is our reaction. This is the reaction we know. If the reaction that we are doing is the inverse of the reaction that we know, or our Kw, you should be able to find the K here. Find the K for our reaction. Remembering that our reaction here is the inverse of the autoionization of water. Once you have done that, we're going to use what we've learned here in our thermodynamics chapter and recognize that delta G naught is equal to minus RT times the natural log of K. And this is going to be the K for our reaction up here. Please remember that your temperature has to be in Kelvin, and use the correct value of R such that you get the units in joules. Once you have done that, please recognize also that delta G is equal to delta H minus T delta S, where this delta G is right here. Our delta H is from the first page. Our T is going to be the temperature initial in Kelvin. Calculate the delta S. Make sure that your units are the same for delta G and delta H, either kilojoules per mole or joules per mole, such that they are self-consistent. And at that point, you are finished with your enthalpy of neutralization lab.